Hi everyone, it's Michael, and today we are going to be learning about the pumping lemma for context-free languages. So we have studied how to prove a language is irregular by having it fail a pumping lemma, but we have not yet learned the pumping lemma for CFLs in class. Right? So as a recap, context-free languages are a language class larger than the class of regular languages. Using it, we can get context-free grammars. So this is what we are talking about today. So this, and this is what we were talking about previously for the previous pumping lemma. So the new pumping lemma that we're learning about today encompasses what was taught previously. So in CFGs, by the way, we cannot use star sign or the asterisk, the vertical line, or the oblique slash, uh, just the slash, I guess, symbol. Like in regular languages. In terms of the CFG itself, we'll now describe what composes a CFG and how that makes it CFL. So in CFGs, they are defined by four tuples where the grammar or the G equals V, sigma, S, and P, where V equals the set of variables or non-terminal symbols, sigma equals the set of terminal symbols, S equals the start symbol, and P equals the production one. So what do all these terms mean? Well, it can be kind of confusing, and I myself, and I assume many of you also like learning more from example than the actual definition. So we'll start off with the example, and then I'll explain it a little bit more. So in this example, for the generation of a language that generates equal number of A's and B's in the form A then to the n and B to the n, context-free grammar will be defined as G equals SA AB, and then S arrow, little a, big A, B, and then A arrow, little a, big A, B, and then the line is kind of like an or, and then epsilon. Epsilon, by the way, if you didn't know, terminates it, or takes it out. So we'll start here. So we start with S because, as you can see here, just the start symbol. And the start symbol gives us this right here, the AAB. So we sub that in. And then, so we have this. So what do we do next? We look at the production rule, and our rule here is that it can be the left or the right. And so we take the left, this one. So we sub it in, and then we get this. Thing is, in the middle here, though, we also have an A, and that's part of our production rule. So we're able to do it again right here. So now, instead of just A, B, B, we A, big A, B, B, B. So again, we could do it, but instead this time we're going to be doing the epsilon. We're able to take it out right here. It's gone now. And the thing is, if we look at what the rules were, we want the number of A's to be equal to the number of B's. So it's AN, BN. So when we put it in power notation, we get A cubed and B cubed. In other words, AN, BN if n equals 3. So as we can see, we generated a context-free language with an equal number of A's and B's using the provided context-free grammar. And just to backtrack a little bit, because I think you might have a better idea of what the start symbol and production rules are. So as you can see here, blue is a set of terminal symbols, like color-coded everything. And these are the things that we're dealing with. But these are the things that actually like kind of matter. These are the things that are we're able to sub these things into. So it'll be like this way, or here I'll draw it out this way. So for the A's, we were able to sub it in with this right here. And for the S's, that's what gave us our starting state right here. And yeah, in this case though, I guess it is important to point out that the starting state here is equal to what we're subbing in, which is why it's pretty straightforward for an example, but that's why they're starting examples, to be honest. Um, Okay, let's move on. Now that we know how context-free grammars can be used to make context-free languages, we move forward with the pumping lemma for context-free languages. So it is important to note that the pumping lemma for regular languages, what we've talked about previously in this class, is very similar to this pumping lemma for context-free languages. So if you already know that one, this will be easier for you, which is honestly pretty nice because they're related somewhat. As a short recap, language is regular if it can be made into a machine such as a DFA or NFA. However, in this case, a language can be proved to be irregular if it does not satisfy it. Pumping lemma. My bad. This is where, in this case. Similarly, the pumping lemma for context-free languages can be used to prove a language if it is not context-free. Before, what we talked about is proving a language is irregular by not having it satisfy the pumping lemma. In this case, if it does not satisfy the pumping lemma, it will be because it's not context-free. So these are kind of just the rules overall of the pumping lemma for context-free languages. So if A is a context-free language, then A has a pumping length P such that any string S where the length of S is greater or equal to the pumping length may be divided into 5 pieces. So if S is equal to the string, then it'll be divided into pieces U, V, X, Y, and Z. And it's important to note, just because the pieces of the string does not make them strings. They're just parts of the overall string. And such that the following conditions must be true. So these pieces must follow these conditions. So U and then VI to the power of I, XY to the power of I, and Z is an A for every I greater than or equal to 0. And this is just pretty much saying that for these powers of I, which are greater than or equal to 0, um, they just have to match these powers. And yeah, so specifically the I and the Y. Here it's saying that for the parts V and Y, the length of these two must be greater than 0. And then finally, final condition is that the length of V, X, and Y is less than or equal to P, the pumping length. Those are the three conditions. And so in order to pass the pumping lemma, all three of these must hold or be true. So the following are the steps to a proof for showing a language is not context-free using the context-free language's pumping lemma. And note, this does use proof by contradiction. So, of course, start off with the proof. That's always important. Assume that A, the language, is context-free. Use the pointer again, right here. So we're saying A to the language. A has to have a pumping length of P. Note all strings longer than P can be pumped. By the way, the absolute value symbols denoted here represent length. So the length of any string longer than P can be pumped. Now find a string S in A such that the length of S is greater than or equal to P, pumping. So dividing this string S into these 5 parts, which are U, V, X, Y, and Z. So we divide it, and then we will have show that UV to the I, X to the Y, and Z is not of, well, epsilon A for some I. And then I, in my notes, myself, I define it as here in UV to the I, X, Y to the I, Z is not within A. So then we consider the ways that S can be divided into UV, X, Y, and Z. And this then separates the proof into cases. So then show how none of these ways, or these cases, can satisfy all of the 3 pumping conditions above at the same time. So if this doesn't work, then we don't even need to check these two. But if this works, then we have to check this one. And then if this one works as well, then we have to check this one. All three of them need to be true for it to pass a pumping limit for a case. Um, and then usually, if for some reason it cannot be pumped from one of these conditions, then there's a contradiction, and it is not a context-free language. So let's move on to an example, why don't we? Show that L equals A to the N, B to the N, and C to the N, and N is greater than or equal to 0. How this is not a context-free language. So following our steps, we will do the following. We will assume that L is context-free, and L must have a pumping length of B. We're just following our steps here from what we went over previously. Now we will find a string S such that the length of S is greater than or equal to P. So we have S equals, and then A to P, B to P, and C to P, where P is representing the pumping length, stated here. Now we will divide S into different parts of U, V, X, Y, and Z. So it is important to notice we'll now break the proof into cases. We must account for all cases and subcases. So we will experiment with different pumping lengths to satisfy the first condition of the pumping limit. Then we'll try to satisfy the other two conditions after. Sorry, it's not as much pumping lengths as much as its combinations, and we'll see in a sec. We'll also now have to make different cases for the proof, as there are different ways to divide S into parts. So in this case, we set P equal to 4. As we stay here, we're experimenting with different pumping lengths, but not just that. Don't forget, we're also going to be experimenting with the different options. We set P equal to 4 and pump S 4 times the string. So kind of do like this. This is just for fun, but if it's a pumping length of 4, we're going to do 1, 2, 3, 4. And what does that mean for the string exactly? So that is fun. Because our string looks like this, and the N is affecting the pumping length, or in this case, P, it'll be duplicating each one. So we have the original A, but then we also the next one, next one, and next one. So 4 pumps means 4 A's, 4 B's, 4 C's. And this gives us two cases that we need to account for. So I already figured out the cases for you guys, but actually the cases are some of the hardest part of the pumping lemma. So if you do want to get better at pumping lemma, you do have to figure out your cases. So case 1, the V and the Y each contain only one type of symbol for the language L. These are the things that we're breaking up into. So parts V and Y each contain only one type of symbol. By these seminoles, going back to our definitions, at the very beginning, we have um, set of terminal symbols. I'm sorry, I almost mixed things up. Blue. That is what we are talking about. It can only contain one of those. So I already did the work for us here, but you just are assigning it. So for the U, we only get an A, one A. V, we only get an A. X, we get multiple though. So we get AA, BBB, BB, and then C. So X actually has 3 different types. Y has one type and it's only a C, and Z has 2 C's, but only one type. And as you can see here, V and Y each only contain one type of symbol. 1, 1, 1A, 1C. So now we can actually test it to see if it satisfies conditions. And if I equals 2, for uvi to the I and xy to the iz, then it becomes uv squared xy to z. And substituted it in and expanded using this chart here, or just the way that we divide to split it up, we get a, b, and c. For entire notation, because that's a lot more organized, a to the sixth, b to the fourth, and c to the fifth. But there's a problem. These should all have the same powers. So because, by the way, that's what it said in the example right here. They're all to the same power of n, so they should be having the same powers, but they don't. Kind of weird, right? We have, because A, B, and C do not all share the same power, they are not epsilon L. They do not belong in the language. Interesting. So what about other cases, right? So our final case, case 2, the V or Y contains more than one type of symbol from the language L. So using this principle this time, we're going to make sure that they contain more than one type of symbol, or, so it doesn't even both of them, for the language L. And again, I did divide it up just for the sake of time, but here we go. So A, and the U's, so U has one type, B has multiple types, as it wants here. So A, B, so two types here this time. X has one type, and Y has one type. So in this case, the Y has one type, and then it's actually the V's that have two types. And the Z's have one type, the C's. So we are satisfying this, and we split up correctly. We'll now test out our way in which we divided S, right here. So if I equals 2 for this pattern, or the way that we split it up, then it becomes uv squared xy squared z. When we sub in these values here into this and expand it based on the powers, this becomes that becomes this. A, B, B, A, B, 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 C, 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 C. Or in power notation, a to the sixth, b to the seventh, c to the fourth. And just like our previous example, these both do not share all the same power, which is what we need in this problem. So therefore, they are not in L. They do not belong in L. So what does this mean exactly? In both of these cases, the resulting string we get does not belong in L, the language, and therefore fails the first condition of the pumping lemma. Because it fails the first condition for both cases, we do not need to check the other two conditions of the pumping lemma. This is a contradiction, therefore the language is not context-free. Cool, thank you. All right, so now that we did everything, I'll just be going over it really quick because we have some more time. Let's go this is everything. We talked about how regular languages are within these CFGs, and CFGs/CFLs are what we're talking about today. These CFLs are composed of 4 parts, and what you mainly have to worry about is what we're starting with in the production. These are the things we're dealing with, the blue, and these are the things that we're kind of using to represent these blue, and then we sub stuff in. And we did the example and just kind of talked about it. We actually learned the rules. So have the pumping length B, and just the general thing is we have these 3 conditions that it needs to pass for the pumping lemma. And what we do, sorry, I was looking for this part. For some power of I, we use it to show that it's not included in the language. And if the example we choose doesn't satisfy, or with one of the cases, or both the cases actually, sorry, if it doesn't pass even just one of these, as we did right now, then pumping lemma does not work with it. So what we did is we followed those basic steps until we get to S equals A to P, B to B, C to B, and then we choose the powers for it to be represented, and we pump it. Sorry, I think it's supposed to be 4 times. It might have been more by accident. And then we got the 2 different cases where V and Y are the same and they each contain only one type, and also V and or Y contains more than one type. So they're not the same amount, and one of them contains, in this case, 2 types, A and B for Y, and then for Y it contains only 1 feet. And in both these cases, in the first place, they aren't in the L. So it doesn't satisfy first condition, and therefore we have a contradiction, sorry. And the language is not context-free. And that is everything. Awesome. Thank you.